All right, welcome to the screencast for Unit 3. This is objective number 3. We're going to talk about how the atomic number, the charge, and the mass are all used to find the number of protons, neutrons, and electrons, whether we're dealing with an atom, an ion, or an isotope. These should not be foreign words to you or foreign vocabulary terms to you, but we will go through what each of them means throughout this objective. So the first thing I want to talk about is the atomic number. The atomic number is the number of protons that element has. This is the largest number that you tend to see on the periodic table in each of the boxes. The elements are listed in order of atomic number. So hydrogen has 1, it's number 1. Hydrogen is number 8, so it has 8 protons. Uranium is number 92, it has 92 protons. So whatever number they are, that is the number of protons. That never changes, at least in these reactions that we're going to talk about. In a standard chemical reaction, the number of protons never changes. So what's interesting about this, the identity of an atom is based on the number of protons. So each element is going to have a different number, and that's how we tell each atom apart. So elements are listed in order by atomic number on the periodic table. So the atomic number always tells you the number of protons. When we look at a regular atom, an atom is neutral. The name or the term atom implies neutrality. So the number of protons is always going to be equal to the number of electrons. So if you have a neutral atom, you know that the number of protons, if it's 8, the number of electrons is also going to be 8 to give it no charge. In an ion, that's when we start to see charges show up. So you have a charged atom. The number of protons doesn't change, but you have gained or lost electrons. So electrons can be gained or they can be lost by the atom, and when it does that, it forms the ion. A positive ion is called a cation, and that's when you have more protons than electrons. So you have actually lost electrons, whether it's 1 electron or 2 electrons or 3 electrons, that'll determine your charge, but you have lost electrons, so you have more positives than negatives. And in a negative ion, you have now more electrons than protons, so you've gained electrons, whether you've gained 1, 2, 3, or 4 electrons, however many you've gained. You form an anion, which is a negative ion. You've heard of these terms or you've seen these terms before. So the number of protons does not ever change, at least for the time being. We're not doing nuclear reactions here. We will in the future where protons will change. But for right now, just go with the assumption that protons never change. So some examples of atoms and ions. When you look at oxygen, oxygen has 8 protons and 8 electrons. It's a neutral atom. There's no charge on it. But if I put oxygen with a 2- charge on it, and notice that I put the charge as a superscript in the top corner, and I put the number in front of the charge, don't put -2. It seems kind of nitpicky, but it actually makes it much easier to tell that there is a charge on it, because if you just put a dash in front of that, you might not be able to see it. So oxygen with a 2- charge, I still have 8 protons, but it has a 2- charge, so it has 2 more negatives than positives. So I have gained 2 electrons to make it have 10. Has 2 more negatives than positives. Regular phosphorus has 15 protons, 15 electrons, so you see there's no charge on it. But the ion of phosphorus is a 3- charge. So if phosphorus has 15 protons, how many electrons would it have to have a 3- charge? Well, you just add 3 to it, and it would have to have 18 electrons then. So you can work through these examples in your notes. We will work through these in class, but go ahead and try them out in your notes. See sodium atom, sodium ion, magnesium atom, magnesium ion, chlorine ion, carbon atom, carbon ion, lead ion, and arsenic ion. Go ahead and try those, and we will work through those together. And then you can also label whether they're ions or atoms. So this slide right here just shows you the difference between an atom and an ion. An atom, they have no charge. The number of protons is the same as the number of electrons, so the atomic number tells you the protons and the electrons. An ion is where you've now lost some electrons, or you have gained some electrons, so it has a charge. The number of protons is not the same as the number of electrons. So gain or lose electrons, and you use the charge to determine the number of electrons that have been lost or gained. Okay, so the next part of this, if I can get it to load up here, is going to be about isotopes. Now, isotopes are in relation to the mass. So we're not talking about charge anymore. We're talking about the mass of the atom. So charge can be used to determine the number of protons and electrons, but how do we determine the number of neutrons that are in the atom? This is where we have to use the mass of an atom is used to, it should say, determine the number of neutrons. The formula for this is mass equals protons plus neutrons. Electrons are actually too small to contribute to mass, so we don't count electrons in the mass of an atom. And just like, or as with the ions, they are gaining or losing electrons, so the charge is going to be affected. Neutrons have no effect on the charge because they are neutral. So when you're talking about ions or the charge, you're dealing with electrons. You're talking about isotopes or the mass, you're dealing with neutrons. So atoms that have the same proton number, but different masses, are called isotopes. So you can gain neutrons and weigh more, you can lose neutrons and weigh less. We're going to watch this video in class, so you don't have to watch it right now. These videos we will go through and watch. So the mass that's listed on the periodic table for each element is actually not a whole number. The mass that's listed on the periodic table is the weighted average of all the known isotope masses for that element multiplied by their percentage found in nature. We will go through and we will figure these weighted averages, so don't necessarily worry about that right now. I just want you to see that it is not a whole number, and that's because it's the weighted average for all the isotopes that are possible, not just one isotope. Isotopes that are more common are going to have more weight in that calculation. So to make your life easier for right now, just round the mass number on the periodic table to the nearest whole number. So 15.9994 would round to 16, 1.0079 would round to 1, and that's going to be your mass. So the mass is protons plus neutrons. So in order to get to 16, my protons plus neutrons must equal 16. For hydrogen, having a mass of 1.0079, my protons plus neutrons would equal 1. You'll always know the number of protons, and you'll always know the mass because that's given to you on the periodic table. So all you'll have to do then is subtract to get the number of neutrons. So the mass number minus the number of protons to determine the number of neutrons. Symbolism is actually pretty important with isotopes. A lot of times you're going to see them written as the element name or the element symbol, and then there'll be a dash, and they'll be followed by a number. That number is going to be the atomic mass. Like, for example, hydrogen -1, so the mass of that would be 1. Oxygen, 15, the mass would be 15. Carbon, 12, the mass would be 12. So the number after is equal to protons plus neutrons for that particular isotope. So oxygen, 15, if it has 8 protons, it would have to have 7 neutrons to have a mass of 15. Go ahead and work through these using your periodic table in your notes, and we will go through and work through them in class just as a review really quick. Remember, charge is determined by changing the electrons. Mass is determined by changing the neutrons. You never change protons. Not all isotopes are stable, so just a little bit more about isotopes. Many will decay into other elements, and they do this sometimes quickly, sometimes slowly. It just depends on the actual stability of that isotope. Carbon-14 is an isotope that we use for radiocarbon dating of fossils. That's how we tell the age of fossils. Uranium-234 is used in nuclear reactors to produce nuclear power. There's a barium isotope where you will swallow it in this liquid form. They give you the barium drink. And they can use it to diagnose acid reflux or stomach ulcers because it'll make you glow on an MRI scan. There's also a radioactive iodine that they can give you that will make your blood glow. And they can see things like kidney stones or tumors and stuff like that throughout your bloodstream. So these isotopes are radioactive because they're not stable, meaning they are going to break down. They are not going to stay this way forever. We will talk about radioactivity in our nuclear unit. So remember, for an ion, you change the number of electrons, that affects the charge, and an isotope, you change the number of neutrons, that affects the mass. You never change proton number, at least not right now. So the last little bit of this is writing things in isotopic notation. Isotopic notation is a way of writing all the information easily for an element, isotope, or for an ion. It's just a way to very easily have a symbol that you can read to tell the number of protons, neutrons, and electrons for anything. So kind of the basic equation is a number, you have numbers in the front and you're going to have numbers in the back. So the numbers in the front, you're going to have a superscript. And that top number is A, that's your mass number. So your mass goes on top. Z is the atomic number. That's the number of protons that goes on the bottom. So your mass number goes on top, number of protons on the bottom. So the bigger number first, and then the number of protons on the bottom. The element, the E, is the element symbol, and then this also has a spot for you to put the charge, just like we have been before. So the charge goes after. If it's an ion, it's going to have a charge. If it's an atom, it won't, so you just leave it blank. And there's a video clip that we can watch in class, but it does take you through how to do a few of the isotopes, or how to write them in isotopic notation. So here's just some diagrams for you. You can see the mass number on the top, the atomic number on the bottom, and then the element symbol, and then the charge. This and this and this are all the same. This is an element because it doesn't have a charge. This would be an ion because it does have a charge. So just kind of the basic setup for isotopic notation, and you'll always do this the same way. So these are the examples that I want you to put in your notes. We will go through these in class. So you need to write this in isotopic notation. So if I tell you the protons, neutrons, and electrons, write the isotopic notation for that element, or for that ion, whichever it might be. Write the following in isotopic notation, and then give the number of protons, neutrons, and electrons. So arsenic 75, you have to know what the 75 means. And here, there's nothing, you don't have any information about a charge or about electrons, so you just have to assume that it is an atom if there's not a charge that's given. So write that in isotopic notation. And then for this one that's written in isotopic notation, take this information and tell me the number of protons, neutrons, and electrons for oxygen, for this particular oxygen ion. And the summary for this objective, oh, hang on, there's one more example. So go through and do this also in isotopic notation. So if I tell you protons, neutrons, and electrons, put that into isotopic notation. And we will work through these in class before I turn you loose doing some practice problems. The summary for this is going to be template number 1.